In a world where most consumers of music listen on wireless earbuds or headphones, are studio monitors even relevant anymore? Should you be mixing exclusively on headphones because that's the way most people will ultimately enjoy your music? There's an ongoing debate about this, but I'd say having both is better than having one or the other. But when you compare the cost and portability of a good pair of headphones with that of a good pair of speakers and acoustic treatment, it's clear that the headphone route is much more accessible. So if you're mixing with headphones, here are 5 tips for you. Thanks to RME for sponsoring this video and supporting audio education. One reason mixing with studio monitors is so expensive compared to mixing with headphones is that you not only need to invest in a pair of high-quality studio monitors, but you also need to invest in acoustic treatment within your listening space. The ultimate goal when setting up any monitoring system for mixing is to build something you can rely on in order to make decisions about what sounds good and what doesn't. As you'll see in a moment, this isn't necessarily the same for headphones as it is for studio monitors. A good pair of studio monitors will usually have a very flat frequency response, meaning what comes out of the monitors will very closely resemble what goes into the monitors from a frequency balance perspective. But when you're mixing with speakers, the acoustic reflections and resonances in your space will alter that frequency balance. In practice, this means you end up needing to spend even more money on acoustic treatment to correct those issues so that the frequency balance is preserved by the time it reaches the listening position. The ultimate destination for all of the signals in my studio is this RME ADI2 Pro FS. It connects to my audio interface digitally, converts the digital audio to analog audio, and feeds my studio monitors and my headphones. The ADI2 has a parametric EQ on each of the studio monitor outputs, which can be used to make adjustments that fine-tune some of the remaining nonlinearities in the frequency response of my system after acoustic treatment has been applied. But as you can see, there's still a lot of work to do in terms of physical acoustic treatment within my room, so I'll almost certainly get more accurate sound from headphones which aren't affected by the acoustics of my room at all. There are several ways to implement corrective EQ, but I prefer this method where it's a piece of hardware in my signal chain rather than a piece of software on my computer, because this workflow allows for separate correction curves for speakers and headphones without the risk of forgetting to switch a preset and without the need to deal with problematic drivers or software. There are also parametric EQs on the headphone outputs of the ADI2, but these aren't necessarily used to target a perfectly flat frequency response as we might target for studio monitors. See, we've grown so accustomed to listening to speakers in a room that when you directly inject sound into your ears with a very flat frequency response using headphones, it ends up sounding different from what you'd expect. Therefore, many modern mixing headphones will not have a flat frequency response, but will rather have a frequency response that attempts to approximate the sound of listening through speakers. There are several targets used in modern headphone production. One is to measure the frequency response of a high-quality speaker in an anechoic free field. Another is to measure the frequency response of a high-quality speaker in a reverberant room from a distance far enough away from the speaker that the indirect sound and the direct sound are equal in level, aka a diffuse field. And in recent years, the Harman target curve has become very popular because it integrates a high-quality speaker, a high-quality room, and human perception and preference. In any case, these curves are far from flat. Many people use frequency response correction for their headphones as well. In fact, there's a Reddit post linked below the video that gives you the specific parameters to put into an RME ADI for several different specific models of headphones in order to get closer to the Harman target curve. In my opinion, I think it's best to listen to the uncorrected frequency response of your headphones because you can take that with you anywhere. That means you can rely on your headphones as a reference in any situation, even if you don't have a corrective EQ curve applied. There's a wide range of options when choosing headphones, but even some of the best headphones out there still cost a fraction of what you'd pay for studio monitors. I'd avoid active noise canceling headphones or wireless Bluetooth headphones, and you can check out the links below if you're interested in learning why these should be avoided. When choosing headphones, it's also important to consider the headphone amplifier that will be used to drive the headphones. Be aware of the impedance and sensitivity of the headphones, and the power and voltage that your headphone amplifier can provide. The sensitivity of your headphones tells you how much sound pressure level could be expected at a given voltage or power input. For example, the sensitivity of the Neumann NDH30 headphones can be found right here in the technical specifications. This specification tells us that you can expect an output of 104 dB SPL when you send a 1 kHz tone through the headphones at 1 volt RMS. Like I said, other headphones may show the sensitivity as dB SPL at a specified power input. The impedance of headphones impacts the power that can be provided at a given voltage from the amplifier. To better understand this concept, let's compare the 32 ohm, 80 ohm, and 250 ohm version of the Beyerdynamic DT770 headphones. This test won't necessarily give you a good impression of how these headphones actually sound, but you will notice a level difference. The higher the impedance, the lower the output level at a given level from the amplifier. This can all be explained by Ohm's Law. V equals I times Z, or voltage equals current times impedance. If we rearrange the equation to I equals V over Z, or current equals voltage divided by impedance, it more clearly shows that at a given voltage, current will increase as impedance decreases. Another relevant formula is P equals V times I, or power equals voltage times current. This means there are two ways to increase the power consumed by the headphones. Either we increase the voltage, or we increase the current. When using a battery-powered device like a smartphone or a laptop, there's a limit to how much voltage can be supplied. Therefore, the only option at that point is to increase the current, which can be done by decreasing the impedance of the headphones, as we just saw through Ohm's Law. Okay, enough math. What does this mean for mixing in headphones? If you're using the headphone amplifier built into the headphone jack of your laptop, you'll probably want to stick to using headphones with high sensitivity and low impedance. Lower impedance means the headphones can consume more power at a given voltage, while high sensitivity means you'll get more acoustic output at a given power input. Trying to drive high impedance, low sensitivity headphones with an inadequate headphone amplifier will result in low output level and perhaps even diminish the low frequency response, as low frequencies require more power to reproduce. And remember, we want a reliable frequency response when mixing, so make sure you have proper pairing of headphones and headphone amplifier. It's important to note that Apple laptops now integrate an adaptive headphone amplifier that can accommodate a wider range of headphone impedances by adapting the maximum output voltage depending on the impedance of the headphones connected to the headphone jack. The headphone amplifiers in the RME ADI2 Pro FS are extremely powerful as the device is connected directly to wall power rather than relying on a battery. They also adapt to various types of headphones through low power mode and high power mode. Plus, the total harmonic distortion and signal-to-noise ratio specs on this thing are unfathomably good, even in the most extreme scenarios. If I hear noise or distortion in the signal I'm listening to, I can confidently assume it's not coming from my headphone amplifier. It's something else earlier in the signal chain. When you listen to a recording on speakers, the stereo image will not be the same as when you listen on headphones. There are a few reasons for this. First, a signal hard panned all the way to the left speaker will be 30 degrees to the left on speakers, giving you a 60 degree stereo width. On headphones, an element hard panned all the way to the left will be 90 degrees to the left, resulting in a total width of 180 degrees. In practice, this means we'll tend to make panning decisions when mixing in headphones that will be too subtle when played back through speakers. On the other hand, panning decisions on speakers will sound much wider when listened on headphones. And there's no real solution except to be aware of this reality and adjust accordingly. The second difference between the stereo image on speakers and headphones is that there will be total isolation between the left and right speaker in headphones that doesn't exist with speakers. With speakers, the left and right ear will hear both the left and right speaker. The left ear hears mostly the left speaker, but also hears the right speaker, albeit quieter and a bit later in time. The right ear primarily hears the right speaker, but also hears the quieter and slightly later signal from the left speaker. The slight delay of the right speaker in the left ear and the left speaker in the right ear can have effects in speakers that can easily go overlooked when listening through headphones. Let's say you have a vocal panned directly to the center, which means the signal level will be equal in both the left and right speaker. When the acoustic signals from each speaker meet at the left ear, they interact at a slight time offset, resulting in cancellations at some frequencies and summations at other frequencies. This is called a time of arrival difference, and it results in comb filtering, where these cancellations and summations resemble a comb when shown on a frequency graph. This will also occur anytime you use a non-coincident stereo technique or certain delay techniques. Meanwhile, you won't hear these cancellations and summations when listening to that same center panned vocal through headphones. Luckily, there are a few things we can do to highlight these problems even when we don't have the luxury of listening through speakers. The first would be to sum the left and right channels to mono, where both speakers play both channels. Then listen for problematic interactions between the two channels. This is a worst-case scenario because the left and right channels now reach the left and right ear equally, so take the results with a grain of salt. You're really checking mono-compatibility here rather than speaker compatibility. Another way to check phase correlation between the left and right channel of your mix is to use a Vectorscope. This type of meter can be accessed in software like RME DigiCheck or in plugin form such as Isotope Insight. Let's send some test signals through this meter to understand what it's telling us. The basic principle of these meters is that there's a dot that will move throughout the graph, leaving a line behind it that traces its path. If I send a low-level 1 kHz tone through the left channel only, we'll see a relatively short diagonal line leaning to the left. Increasing the level will make the line longer, decreasing the input level will make the line shorter. Alternatively, we can turn on the auto gain feature to automatically increase the input gain over the course of a few seconds and fully utilize the graph. Now, I'll duplicate this test signal, sending one copy to the left and one copy to the right. But for now, they're equal in level, which creates a vertical line. Notice that the correlation meter on the bottom reads +1 when the signal to each channel is in polarity. When I flip the polarity on one channel, the left speaker and right speaker will be in opposite polarity, the trace will become horizontal, and the correlation meter will read -1. Let's change the test signal to pink noise, which contains energy across the frequency spectrum, more similar to music. To visualize what happens when the left and right speaker interact at one ear at a slight time offset, let's delay the right signal. Now we can see some frequencies cancel out and others sum together, and that creates a comb on the frequency graph. This can also be seen with a frequency sweep, but to avoid the risk of diving too deep into the secrets of the universe, let's get back into what this means for mixing music with headphones. If you play a professionally mixed stereo record through a Vectorscope, you can expect some variation on the graph. That's okay, that's what makes it stereo. But you'll notice that the formations will typically maintain a somewhat vertical orientation, indicating that the left and right channels are mostly correlated in terms of polarity and phase. This isn't always the case though, so use it as a guide, not as a rule. You can use this type of meter on pairs of individual instruments in your mix or on the stereo mix as a whole. This will help you to identify serious interference that might occur between the left and right channel when summed to mono or when played through speakers. Some monitoring devices also offer a crossfeed feature, like the one built into the RME ADI2. This will send some of the left channel to the right channel at a slight delay, and vice versa. The ADI2 uses the Bauer binaural method, which I'll admit is a bit over my head, but if you're interested in learning the technical details, I'll leave a link to the article below. In practice, this feature offers a headphone listening experience that's more comparable to a speaker listening experience while mitigating the comb filter effects that I just discussed. It's not a bad idea to drag and drop the audio file of a great sounding mix into your session as a reference. I'd recommend finding a mix in a similar genre that you can use as a guide from the very beginning. You wouldn't want to mix a country song with metal recording as your reference, just as you wouldn't want to mix a pop song with a classical recording as your reference. Having one or two tracks will help you find your bearings before setting out on the mixing journey, and you can return to it throughout the process to make sure you're generally on the right track to make a mix that conforms to basic genre standards, assuming that's your goal. Some tools, such as isotope tonal balance, can help you more objectively understand the way your mixes might compare to other mixes in similar genres. You pick the genre, and the plugin will analyze the mix compared to a target curve. In addition to having a good reference track in your session, it's also important to develop a good reference for what sounds good and what doesn't sound good for the particular genre you're mixing. This can be done by listening to lots of music on headphones and by training your ears with the method I've discussed in other videos in this channel. I'll leave some links below if you're interested in learning more about the ear training method for audio engineers. While the tips I've shown you here can help if you're mixing exclusively on headphones, there are some things that speakers really can help with, even if your audience will ultimately listen in headphones anyway. For one, you'll never feel the haptic sensation of a kick drum in your chest while listening through headphones. Only speakers can reproduce that feeling. There's also something to be said about checking reverb on speakers, because the additional noise floor and reverb within your room may show you that the really subtle reverb you added in headphones is completely imperceptible when played back in a real room. You can't walk around your room or outside your room to listen to how your mix changes with headphones. And that's a good thing if you want to adjust something that you can't reach from the sweet spot, but listening outside the sweet spot can also help you refine your mix so it stands up better to those real-world situations. Rather than setting mental notes to not pan too much in headphones, it's better to check your mixes on speakers. Rather than relying on EQ profiles to know how it will sound in a car, in earbuds, or TV speakers, it's just as good to print your mix and listen to it on those systems. But that's an exercise that takes time, so having the tools I discussed in this video will really help from a workflow perspective. The ADI2 offers separate correction EQ curves for my studio monitors and headphones. The headphone amplifiers are extremely high quality, and they adapt to a variety of headphone impedances. ADI remote software provides quick controls for checking monocompatibility or crossfeed, and DigiCheck provides a variety of meters for better understanding the sound that comes out of my headphones. Finally, reference tracks, ear training, plugins like tonal balance control, and testing on a variety of speakers all guide my decisions toward achieving a target sound. Over time, you will learn the effect of your headphones, and you'll develop an ability to compensate to make mixes that sound good on a variety of speakers without the need to test. Practice is where you'll get the biggest improvement, and you can practice with the basic tools you've already got. In this video that's on your screen now, you'll learn about the ear training method that I mentioned earlier. It will help you to identify frequencies by ear and start using EQ with confidence. I'll see you there.